All right, let's take a look at the practice test. For the instructions, we're asked to find the magnitude and direction angle. So for the first problem, we have our vector v, and this is given to us in component form. So we have a horizontal component of 24 and a vertical component of 32. What I would do is sketch this guy. So let me write out that my vector v, again, in component form. Let me set up these angle brackets here. So the horizontal component is 24 and the vertical component is 32. So again, what does this mean? This tells us, if we have it in component form, that the initial point is going to be at the origin or 0, 0, and the terminal point is going to match this right here. So the x value of the terminal point is going to be 24. It matches the horizontal component. And then the y value of your terminal point is going to be 32. It matches the vertical component over here. So what you could do after you sketch the graph, you want to first find the magnitude. So basically, that's just the length of this vector right here. Okay, so let me put that this is the vector v like this, and we'll use these vertical bars to denote that we want to find the magnitude of our vector v. And so this is going to be equal to what? Again, if I wanted to find the distance between this point and this point, what would I do? Remember, your distance is equal to the square root of, you have x sub 2 minus x sub 1 quantity squared, plus y sub 2 minus y sub 1 quantity squared. Okay, well, this is pretty simple because one of the points you're working with is 0, 0. So essentially, you can get rid of this, and you can get rid of this, and you can rename this to x and rename this to y. So essentially, the distance is going to be the square root of x squared plus y squared. So translating that over into our terminology with vectors, this is going to be the square root of the first component squared, or you could say the horizontal component squared, so 24 squared, then plus your second component squared, or you could say the vertical component squared. So that's really all it is. So just key this into your calculator, or we could do it over the course of a few steps if you want to. So we can say this is equal to the square root of 24 squared. That's going to be 576. 32 squared is 1,024. If you add those guys together, you're going to get 1,600. And so the square root of 1,600 is going to be 40. So let me actually erase this and just put that the magnitude of my vector v is going to be 40. Now, the more difficult guy to find is the direction angle. So basically for that guy, you're thinking about this angle here. So between the x-axis and your, in this case, position vector. So let's say that this is our direction angle theta. And so how do we find this? Well, all you really need to do is set up your little tangent guy there. Let me draw a right triangle here so this is crystal clear. So this would be our right angle there. And essentially, if you think about the tangent of theta, so let me write this out. So the tangent of theta, this is equal to, you have your opposite, okay, which in this case, the length here of this side is going to be 32. So let's put 32 over your adjacent. So the length here is going to be 24. So this is how you're going to set them up. It's just not always going to work out exactly like this, because if you're not in quadrant 1, like we are here, you're going to have some detective work that you have to do. So we have the tangent of theta is equal to 32 over 24. Okay, so the first thing I would do, since this is a tutorial, I would simplify this fraction. If you're just going to key this into your calculator with the inverse tangent function, then don't worry about it. So 32 and 24 are each divisible by 8. 32 divided by 8 is going to be 4. 24 divided by 8 is going to be 3. So I'll just say that theta is equal to the inverse tangent of this guy up here, which is 4/3. And let's move this up here. I'm just going to key this into my calculator, and I get about 53.13 degrees. So let's say this is about 53.13 degrees. So this would be my magnitude for my vector v. It's going to be 40. And then my direction angle theta is going to be about 53.13 degrees. All right, let's take a look at problem number 2. So here we have our vector p, which is given to us in component form. The horizontal component is 32. The vertical component is -1. So again, let me write that my vector p in component form. The horizontal component is 32, and the vertical component is -1. So the easier thing to do is to figure out what is the magnitude of my vector p, and essentially it's just the square root of the horizontal component squared, so 32 squared, plus the vertical component squared, so -1 squared. 32 squared is 1,024. -1 squared is going to be +1. So if you add 1,024 and +1, you get 1,025. Now this would be really easy to simplify with your calculator. So 1,025, you see that ends with a 5. So you can divide it by 5 and you're going to get 205. Then that ends with a 5, so divide by 5 again, you're going to get 41. So you could really say that this is 25 times 41, and we know that the square root of 25 is 5, so we can just say that this is going to be 5 times the square root of 41 for the magnitude of the vector p. Okay, the other guy to figure out here, which is the direction angle, is a lot more complicated because your angle, theta, is going to lie in quadrant 4. Okay, so these are going to be more time consuming. You have to do a lot of detective work. I'm going to do this as simply as possible. Typically, what your book will do is just say, okay, well, the tangent of theta is equal to, you take your vertical component, which is -1, over your horizontal component, which is 32, and then you use your inverse tangent function. But because the inverse tangent function, if you plug in something that's negative there, you're going to get something in quadrant 4, and you're going to rotate clockwise, okay? So I think that kind of confuses people. So what I'm going to do here is I'm going to get rid of this, and I'm going to think about this in a different way. So the first thing is we know that one complete rotation, so let me just do this like this, this would be 360 degrees, okay? All I need to do is take that 360 degrees and subtract out the part that I don't want, which is this part right here, this angle, okay? So you can call that beta or alpha or whatever you want to do. Let me get rid of this. Let me just call this angle right here beta, and I can make a simple right triangle here. And forget about the fact that this opposite here would be -1. I'm just going to say it's +1, okay? And then this guy right here, this adjacent, would be 32. So I'm just going to say that the tangent of beta is equal to, again, I'm just working with positive numbers here. So let's say that this is 1 over 32. And so the inverse tangent function would be used. So you could say that beta is equal to, we're going to say the inverse tangent of this 1 over 32. So key that into your calculator, and if you round to the nearest hundredth, you're going to get about 1.79 degrees. So let me put this over here. I'm going to put that beta is approximately 1.79 degrees. Now you could write this in to your little sketch here if you want. So we'll say that this is about 1.79 degrees. So once you know that you want this full rotation here, which is 360 degrees, minus this piece right here, which is 1.79 degrees, you're basically good to go. So the direction angle theta here is going to be approximately 360 degrees minus this piece right here. Again, we called that beta, so that's about 1.79 degrees. So this would give me an approximate value for my direction angle theta of 358.21 degrees. So let's say this is about 358.21 degrees. All right, let's take a look at problem number 3. So here we have our vector k given to us again in component form. So the horizontal component is 42. The vertical component is 44. So let's just say that my vector k, again in component form, the horizontal component is 42. The vertical component is 44. Okay, so the magnitude of my vector k, again, is just the principal square root of, you're going to go 42 squared plus 44 squared. Let's just do that in a calculator. So punching that in, you're going to get 1,764 for 42 squared. You're going to get 1,936 for 44 squared. If you add those together, you're going to get 3,700. Okay, so to simplify this, you see that it ends with 2 zeros. So you could write this as 37 times 100. And 100 is a perfect square. So you could basically say that it's 10 times 10. So I'll say that this is 10 times the square root of 37 for the magnitude of my vector k. Now for the direction angle, again, this is very straightforward because we are going to have an angle that's going to be in quadrant 1. So you can just drop this down here if you want to make a little right triangle. But essentially this is the easiest case because you can just use your inverse tangent function immediately. So the tangent of theta is equal to, this is your opposite, so it's just the vertical component of 44 over your adjacent, which is the horizontal component of 42. Now here you could divide each part by 2. So 44 divided by 2 is 22, and 42 divided by 2 is 21. All right, so let's just say that theta is equal to the inverse tangent of this guy right here, so 22 over 21. Let's key that into the calculator. And if I round to the nearest hundredth, I get about 46.33 degrees. So let's say that theta is approximately, let's go 46.33 degrees. All right, let's take a look at problem number 4. So here we have our vector CD. Now this vector is not given to us in component form, so we would want to find that before we do any additional work. So notice that the order of the letters here is going to be important, right? So the C is listed first, so that's your initial point. The D is listed second, so that's your terminal point. If this had been vector DC, it would be reversed, right? So D there would be the initial point and C would be the terminal point. So looking at this, you see that for your point C, you have -8, 6. For your point D, you have -4, -5. Okay, so essentially all you're going to do to write this in component form, it's very simple. You're going to do terminal minus initial, okay? So you're thinking about the horizontal component first, and that's coming from the x values here. So the terminal is -4, and the initial is -8, okay? So you're going to do -4 minus a -8. So that's going to be the horizontal component. And then for the vertical component, now you're going to do, again, terminal minus initial. So -5 minus 6. So that's all you're doing. It's very simple. So -4 minus the -8 is -4 plus 8. So that's +4. So let's put 4 there. -5 minus 6 is -11. So maybe I'll tighten this down a little bit and write it more cleanly. So this guy right here in component form, you have 4, -11. Now, your book at this stage might rename this using a lowercase letter. So you might say something like the vector CD is equal to this guy right here, which is equal to some vector V or some vector U. You can rename it if you want, but for the sake of this tutorial, I'm just going to keep it very simple. So let's go ahead and copy this, and let's come down to our little sketch, and I'm just going to call this the vector CD. Again, if you wanted to, you could rename this and say this is the vector V. That's going to be up to you. So let's just stay with this guy right here. So the first thing is I just want to find the magnitude of this guy. And this is going to be the principal square root of, you're going to take this horizontal component, which is 4, and you're going to square that, so that's 16. And then plus you're going to take this vertical component, which is -11, and you're going to square that. So -11 squared is 121. So 16 plus 121, that's going to be 137. And 137 is a prime number, so you're not going to be able to make that any simpler. Okay, let's think about the direction angle here. So we're going to see that we're going to have a direction angle that's going to be in quadrant 4. So again, another tricky situation. So this right here is your direction angle. Let's just call it theta. So again, all you have to do is think about, well, a complete rotation. So let's just say we did something like this. This is 360 degrees, okay? So all I need to do is take 360 degrees and then subtract out this part right here. That's what I don't want, okay? So let's just call that angle beta, like that. Let me make the beta a little bit better. So something like that. So let's just go ahead and say that the tangent of this beta is equal to, this is your angle right here. So it's the opposite, which is this guy right here. So it's -11, but I'm just going to use +11 just to keep it simpler. And then the adjacent is going to be this guy right here, which is going to be 4. So when we think about the beta here, it's the inverse tangent of this guy right here, which is 11/4. So let's key that into the calculator. And I get about 70.02 degrees. So let me get rid of this. And I'm going to say that beta is about 70.02 degrees. So let me actually get rid of this, and I'll just say this is about 70.02 degrees. Okay, so basically we know that all the way around would be 360 degrees, and I just need to subtract away 70.02 degrees, and that looks like multiplication, so let me make that a little bit cleaner there. So let's say that my direction angle theta is approximately 360 degrees minus 70.02 degrees. So that would give me about 289.98 degrees. So let's say that's my direction angle, about 289.98 degrees. All right, let's take a look at problem number 5. So here we have the vector PQ. And again, it's not in component form. So your initial point is going to be at 1, 8. Your terminal point is going to be at 8, -7. So again, to put this into component form, let's go terminal minus initial. So we're going to go 8 minus 1. So terminal minus initial. 8 minus 1 would be 7. And then we're going terminal minus initial. So -7 minus 8 is going to be -15. So this right here would be my vector PQ. again, in component form. If you want to, you can rename this at this point. You could say this is the vector v. Again, that's going to be up to you. I'm just going to keep it simple. So let's come down here and just paste this in like this. And so what I'm going to do first is find the magnitude of this vector PQ. So this is going to be the principal square root of 7 squared is 49. Negative 15 squared is 225. So we're going to have 49 plus 225 under here. So that would be 274. Now, if you divide this by 2, you're going to get 137, which we already know is a prime number from the last example. So really, you're not going to be able to simplify this. So this is just going to be the square root of 274. Okay. So now we need to figure out, again, the direction angle. So we are in quadrant 4 once again. So remember, it's 360 degrees to go all the way around. And you just want to subtract away this part right here. Okay. So that's all you're doing. Let me draw this a little bit cleaner here. So I want to find theta. So that's going to be this angle right there. So let's say this is theta. So we'll say theta is approximately, let me make that symbol a little bit better, 360 degrees minus whatever this guy is right here. So let's just, again, call this beta. So minus beta. So how do I figure that out? Again, you can just make a little right triangle here. And then you could say the tangent of this angle beta is equal to, again, the opposite here would be this guy right here. Now, again, I'm not going to put negative 15 in. I'm just going to put positive 15. I'm just going to keep it simple because of how the inverse tangent function works. And then I'm going to say that my adjacent, which is up here, that's going to be 7. So let's go ahead and say that beta is equal to the inverse tangent of this 15 over 7 like this. And that's going to be about 64.98 degrees. So let's say that beta is going to be about 64.98 degrees. So let me put this up here so we can do our subtraction. So 64.98 degrees. So let's key this into the calculator. 360 degrees minus 64.98 degrees. And that's going to give me about 295.02 degrees as an approximate value for my direction angle theta. Let me make that 5 a little bit better. All right, let's take a look at problem number 6. So here we have our vector PQ. And again, this is not given to us in component form. So for P, which is the initial point, we have negative 3, 9. And then for Q, which is the terminal point, we have 2, 10. So let's put this in component form. And maybe I'll just do this down here so I don't have to rewrite it. So my vector PQ, again, if you want to rename this to V or W or something like that, you can do that. Most books will do that. We'll say this is equal to, again, in component form, terminal minus initial. So if you look at your terminal, it's going to be 2 minus your initial, it's negative 3. So this would be 2 minus a negative 3, and 2 minus a negative 3 is 2 plus 3, so that's 5. Then for this guy right here, for the vertical, you go terminal minus initial. So 10 minus 9 would be 1. So that's really all it is to put this in component form. So let's grab this, and we'll just paste this in here. So we have our little sketch. And again, for the magnitude of this vector PQ, let's go ahead and say this is the square root of, you're going to go 5 squared plus 1 squared. So 5 squared is 25, 1 squared is 1, 25 plus 1 is 26. Now 26 is really just 13 times 2, so you really can't simplify that. So the magnitude of this vector PQ is going to be the square root of 26. Now for the direction angle, again, you're going to have something that's going to be in quadrant 1, so it's very, very simple. Again, if you form a little right triangle here, you could say that the tangent of theta is equal to, again, the opposite here is going to be 1, and the adjacent here is going to be 5. Okay, so just take your vertical component, which is 1, over your horizontal component, which is 5, and then you could just do your inverse tangent function here with 1/5 as the argument. So let's say theta is going to be equal to this, and this is going to be approximately, I get about 11.31 degrees. So 11.31 degrees, just rounding to the nearest hundredth. So let's just say that we'll erase this right here, and that theta, the direction angle, is approximately 11.31 degrees. All right, for the next few problems, the instructions tell us to write each vector in component form. So before we jump into the problems, I want to go over this again. This is something we talked about in the lesson, but you might have forgotten or not fully understood at the time. So when we think about this guy, we have our vector u written in component form with a horizontal component of a and a vertical component of b. So we can see that the terminal point there, again, the coordinates are a comma b. Okay, so looking at the right triangle that's formed, this length of this side is going to be b, the length of this side is going to be a, and then the length of the hypotenuse is the magnitude of the vector u. So thinking about my direction angle theta, what we could say is that the cosine of theta is equal to, you have your adjacent, which is a, over the hypotenuse, which is the magnitude of your vector u. Then you can say that the sine of theta is equal to your opposite, which is b, over the hypotenuse, which again is the magnitude of your vector u. Let's grab these real quick. And I'm just going to paste this in for our first problem here. What we're going to do is solve this for a, and we're going to solve this for b. That way we can find the component form. So to do that, in each case, I'm just going to multiply both sides by the magnitude of the vector u. So we'll say that a is equal to the magnitude of the vector u times the cosine of theta. And then b is equal to the magnitude of the vector u times the sine of theta. So a very simple formula. Let's get rid of this and drag this up here so we can just reference it, although the name is going to be different. Maybe I'll just drag it right there. Okay, so for problem 7, we have the magnitude of the vector m is equal to 50, and the direction angle theta is 342 degrees. So we want to find the component form. So in other words, we would say m is equal to, we're going to have a horizontal component, and then we're going to have a vertical component. So this is a comma b. Okay, so how do we find a? Again, it's the magnitude of the vector you're working with. In this case, it's the magnitude of the vector m times the cosine of theta. So the magnitude of the vector m is going to be 50. Let's just plug that in. And then you want the cosine of 342 degrees. So this is something I would just punch into the calculator. And if I round to the nearest hundredth, I get about 47.55. So let's just say that this is about 47.55. Okay. Now for b, you're just going to do the same thing. So the magnitude of, in this case, the vector m, that's going to be 50, and then times the sine of your direction angle theta. So the sine of 342 degrees. Let's just key this into the calculator. And I get about negative 15.45 if I round to the nearest hundredth. So let's put this as about negative 15.45. So that would be your component form for the vector m. Okay, let's take a look at problem number 8. So we have the magnitude of our vector a is equal to 61, and then we have our direction angle theta, that's 120 degrees. Now let's write this up here. So for the vector a in component form, again, typically you use a here and you use b here. These are just stand-ins or placeholders. This a right here is not the same as this a right here. This is the name of the vector. This right here is for the horizontal component. So please don't get confused by that. So let me actually paste this back in so we know what we're doing here. So this would be the magnitude of the vector. In this case, it's a. So let me write this out. So a, again, this is the horizontal component a, not the vector a. This is equal to the magnitude of the vector a, and then times the cosine of the direction angle theta. So this right here is going to be 61, and then this right here is 120 degrees. Now you could just key this into your calculator and get it that way, or you can say that 120 degrees, if you take the cosine of that, you're going to have negative 1/2. So this right here, you could just say this is negative 61 over 2. So you could say, let me write this over here. So for the component form of the vector a, this is going to be negative 61 over 2, or of course you could say negative 30.5 if you wanted as a decimal. So let's put comma. Let me actually get rid of this from up here. We won't have enough room. For the b part, we have the magnitude of the vector a, and then times the sine of the direction angle theta. So this right here is 61, and this right here is 120 degrees. So we know the sine of 120 degrees is going to be the square root of 3 over 2. So really this would just be 61 times the square root of 3 over 2. So let me close that down like that. Of course, you could approximate that if you wanted to. And if you round to the nearest hundredth, you would get about 52.83. So if you want to write it as a decimal, you can say that your vector a in component form, you would have negative 30.5. So that's an exact value there. And then this right here would be an approximate value. So we would say 52.83. So either way you want to write it, with the exact values here, or here, this is an exact value, but this is an approximation. So it's going to be up to you. All right, let's take a look at problem number 9. So here we're given that the magnitude of my vector n is 66 and the direction angle theta is 45 degrees. So we want to find the component form. So for the vector n, let's just go ahead and set it up like this. So this is your horizontal component. This is your vertical component. And essentially, this is going to be really easy because if you think about the cosine of 45 degrees, well, that's square root of 2 over 2. But then also the sine of 45 degrees is exactly the same. It's square root of 2 over 2. So for this one, we know that this is going to be the magnitude of the vector n, which is 66, times the cosine of that direction angle, and that's 45 degrees. So this is square root of 2 over 2. So we would say this is 66 times square root of 2 over 2. So this would cancel with this and give me a 33. So this is 33 times square root of 2. Now, I'm going to get the exact same thing over here. Why? Because now I have the magnitude of my vector n, which is 66, times the sine of 45 degrees, which again is square root of 2 over 2. So 66 times square root of 2 over 2 is going to get me right back to this 33 times square root of 2. So this would be my component form for the vector n. All right, let's take a look at problem number 10. So we have the magnitude of our vector m, that's going to be 78, and the direction angle theta is 330 degrees. So again, in component form for the vector m, for the horizontal component, you're going to take the magnitude of your vector m, which is 78. You're going to multiply by the cosine of this direction angle theta. So that's 330 degrees. Now, when we think about the cosine of 330 degrees, again, this is going to have a 30-degree reference angle. So the cosine of 30 degrees is square root of 3 over 2, right? Now, we're in quadrant 4, so this is still going to be positive. So this is just the square root of 3 over 2. Now, 78 divided by 2, that's going to be 39. So this would be 39 times the square root of 3. Now, if you want to approximate that, you can say that it's about 67.55 if you want to round to the nearest hundredth, so you can put that in that way if you want. Let me actually list it both ways in case somebody wants to do it that way. So this would be about 67.55. So then this guy right here, you would just do the magnitude of your vector m, which is 78, and then times the sine of 330 degrees. Again, it's a 30-degree reference angle. It's going to be 1/2 for the sine of 30 degrees, but you're in quadrant 4, so this is negative. So this would be negative 1/2. 78 divided by 2 is going to be 39. So this would just be negative 39. So this would be negative 39. So let me close that down like this. Let me put negative 39 in here. So either way you want to list this, if you want to use the exact values, or if you want to approximate this one, it's going to be up to you. All right, let's take a look at the practice test. So for the instructions, we're asked to find the resultant using the triangle method. So first and foremost, when we say we want to find the resultant, or sometimes the book will say the resultant vector, this just means we're finding the sum of 2 or more vectors. Now, when we talk about the triangle method, this is a way to show the addition of vectors geometrically. So we're going to do this on a coordinate plane. So for problem 1, we're given this vector A, and it's in component form. So the horizontal component is -5, and the vertical component is 1. Let me make that bracket a little bit better there. Now, the vector B is also in component form. We have a horizontal component of 6 and a vertical component of -8. So what I'm going to do is come to a coordinate plane. And before I show you this stuff right here, let's just do this algebraically. It's a very simple process. So to find the resultant, or again, you could say the resultant vector. So I'm adding the vector A to the vector B. Then basically this result is going to be a vector where we just sum the horizontal components. So -5 plus 6. And then we're going to sum the vertical components. So 1 plus -8. Let's just go ahead and crank that out real quick. So this is going to be -5 plus 6 is 1, and then 1 plus -8 is going to be -7. So this right here would be our resultant vector in component form. So the horizontal component is 1, and the vertical component is -7. So how can we get this result using a coordinate plane? Well, basically, you're going to start with one of these. I'm just going to pick the vector A. You could have picked the vector B. It's really up to you. So I'm going to take this vector A, and I'm going to sketch this guy in standard position. So that means that the initial point is at 0, 0, or the origin, and the terminal point is given right here. So this is going to be -5, 1. So that's very straightforward. You shouldn't have any problems with that. Now, here's where it gets a little bit tricky. You're going to take your vector b, and now instead of having an initial point at the origin, you're going to have an initial point at the terminal point for your vector a. So in other words, the initial point will be at -5, 1. Now you need to figure out where is this terminal point going to be. And the way you do that is you basically say, well, I'm at -5, 1 to start. I'm moving to the right by 6 units. So -5 plus 6 would be 1. Okay, so that's my x location. And then I'm moving to the left by 8 units. So 1 minus 8, or 1 plus -8, is going to be -7. So that's going to be my y location. Okay, so that's my terminal point. Now, once you have that information, you basically have your resultant vector. So the way this works is that it's going to be sketched where the initial point is at the origin, and the terminal point is at that guy you just found, so 1, -7. So that's how you can figure that out geometrically. This is how you can do it algebraically. Either way, you do have to do some addition, but this is just a way you can show this, and your teacher will sometimes ask you to put this down on a coordinate plane just so you understand the concept. All right, for the next problem, the instructions are going to change a little bit. Now we want to find the resultant using the parallelogram method. So this is just another way to show this geometrically. So for problem 2, we have our vector A given to us in component form. So the horizontal component is 4. The vertical component is 5. Then we have our vector B, also given in component form. The horizontal component is 6. The vertical component is -8. Okay, so coming to the coordinate plane, again, I'm just going to paste this in. And I'll just perform this operation now just to get it out of the way. So the resultant vector, again, if I do the vector A plus the vector B, let's go ahead and say it's going to be the horizontal components being added together. So 4 plus 6. And then the vertical components being added together. So 5 plus -8. Let's close that down. So let's crank this out real quick. 4 plus 6, we know that's 10. 5 plus -8, that's going to be -3. So how do we use this parallelogram method? It's a little bit different than what we just saw, but you get the same result. So basically, you're going to sketch vector A and vector B in standard position. So in each case, the initial point is at the origin, or 0, 0, and your terminal point is given here, right? So for the vector A, the terminal point is here. So this is at 4, 5. For your vector B, the terminal point is here. So this is 6, -8. So the main thing is you're going to take this side right here and basically slide it down to create this side right here. And maybe I should have done that in a lighter color so it shows up better. And then you're going to take this side right here and slide it down to create this side right here. So the main thing is once you've created those sides, you just need to find this point right here. And again, you can always do that with this addition. If I'm starting here, and I want to sketch this guy right here, well, all I need to do is say, well, it's going to be 4 plus 6, or 10, and then 5 plus -8, which is -3, right? So you're just going back to this simple addition to get this guy right here. So you get this point that allows you to create this side and this side. So you complete the parallelogram, and then this guy right here, this is going to be your resultant vector, okay? Now, the other way you could have done this, again, you could have sketched your vector A, and then you could have sketched your vector B like this, and you see that you would have ended up with the same result. You also could have done this a different way. So let's say that you chose to sketch vector B first, and then you sketched vector A. Well, again, here's your resultant vector there. So however you want to do this, there's lots of ways to show this graphically. It's very easy to do algebraically. Our resultant vector here, the component form, the horizontal component is 10, and the vertical component is -3. All right, for the next few problems, we're going to change the instructions up. Now we're going to find the component form of the resultant vector. For problem 3, we have 2 that is multiplied by the vector f plus 6 that is multiplied by the vector b. So you have your vector f that's given in component form. You have a horizontal component of -3, a vertical component of 9. You have your vector b, which is also given in component form. You have a horizontal component of -7 and a vertical component of -1. Okay, so if we want to find 2 multiplied by the vector f, then plus 6 multiplied by the vector b, what do we do? So first, I'm going to deal with this scalar here. So this 2 that's being multiplied by the vector f, you're just going to end up multiplying 2 by each component. So let me show this fully. So I'm going to put a 2 out in front of this vector. So you have -3 and 9 as the components there. Let me put a plus sign. You're going to have this 6 that's going to multiply each of these components in your vector b. So let's put this 6 out in front. And let's put -7 and then -1 inside here. Let me put an equal sign here. And I'm going to drop down just a little bit. So basically, to show this fully, I'm just going to say that it's going to be 2 times -3. and then 2 times 9 inside. You don't need to do this each time. You can just do it mentally, but just for the sake of the tutorial, I'm just going to show all the steps. So then for this one, I'm going to go 6 times -7, and then 6 times -1 like this. So let's say this equals, you're going to have 2 times -3, that's going to be -6, and then 2 times 9 is 18, and then plus over here, 6 times -7 is -42, and then 6 times -1 is -6. So now we've gotten this into a form that's pretty easy to work with. We know that if we have one vector plus another vector to find what we call the resultant or the resultant vector, you're going to add the horizontal components. So -6 plus -42, that's going to be -48. And then we're going to sum the vertical components. So 18 plus -6, that's going to give me a positive 12. So the resultant vector here in component form is going to have a horizontal component of -48 and a vertical component of 12. Okay, let's look at problem number 4. So we have 9 times the vector u plus 8 times the vector b. So I'm going to go a little bit faster on this one because it's a very simple concept overall. You have your vector u given in component form. The horizontal component is 3. The vertical component is -10. Again, the vector b, also given in component form, the horizontal component is -11, and the vertical component is -5. So to set this up, let's go 9 times the vector u plus 8 times the vector b. This is equal to, let's put a 9 out in front of this guy right here. So your components, you have 3 and then -10. And then let's go plus. You're going to put an 8 out in front of this vector here. So for the components, again, -11 and -5. So I'm going to go a little bit quicker like I just mentioned. I'm not going to put this inside. I'm just going to think about, okay, 9 times 3 is going to be 27. And then 9 times -10 is going to be -90. And then plus 8 times -11 is going to be -88. And then 8 times -5 is going to be -40. Okay, at this point, what you want to do is add the horizontal components. So 27 plus -88, that's going to be -61. And then add your vertical components. So -90 plus -40, that's going to be -130. So this is my resultant vector. And basically in component form, the horizontal component is -61 and the vertical component is -130. All right, let's take a look at problem number 5. So we have 5 times the vector f plus 5 times the vector v. So for the vector f in component form, we have a horizontal component of -5 and a vertical component of 1. And then for the vector v in component form, we have a horizontal component of 2 and a vertical component of 12. So let's say that 5 times the vector f plus 5 times the vector v is equal to, I'm going to put a 5 out in front of this, so a 5 out in front. So you have -5 and then 1 as your components. And then you have a plus sign. I'm going to put a 5 out in front of this. So the components, you have 2 and then 12. So again, I'm going to go a little bit quicker here. I think we know at this point that the 5 is going to be multiplied by each component here, and the 5 is going to be multiplied by each component here. So 5 times -5 would be -25, and then 5 times 1 would be 5. Then plus 5 times 2 would be 10, and then 5 times 12 would be 60. Okay, so we got this far. Now what do? Well, if we're trying to add these two vectors together, basically you add the horizontal components. So -25 plus 10, that's going to be -15. Then you add your vertical components. So 5 plus 60, that's going to be 65. So the resultant, or again, the resultant vector, if you want to say it that way, we're going to have this in component form where the horizontal component is -15 and the vertical component is 65. Okay, let's take a look at problem number 6. So here we have -4 times the vector u, then minus 9 times the vector v. Now, a lot of times if I see subtraction, I'll just change it to addition of the opposite. It's perfectly legal. You have your vector u here. In component form, you have a horizontal component of 11 and a vertical component of 6. Then you have your vector v also in component form. So the horizontal component is 2 and the vertical component is -5. So let's say that we want -4 times the vector u. Then I'm going to go plus -9 times the vector v. And you can go minus if you want. I just like to do plus negative. So let's go ahead and say this is equal to, I'm just going to stick a -4 out in front of this vector here. So you've got 11 and then 6 as the components. So now I'm going to go plus, because I've written this as addition of the opposite. This guy is going to be -9. And then I'm going to set this up with these components here. So 2 and then -5 inside. So all I'm going to do now is just multiply -4 times 11. That's going to give me -44. And then -4 times 6, that's going to give me -24. So that part's done. Then I have my plus. So I'm going to go -9 times 2. That's going to give me -18. And then I'm going to go negative 9 times negative 5. That's going to give me 45. So at this point, we're going to add the horizontal components. So negative 44 plus negative 18, that's going to be negative 62. And then negative 24 plus 45, that's going to be 21. Okay, so my resultant, or again, the resultant vector, if you want to say that, in component form, the horizontal component is negative 62, and the vertical component is 21. Okay, let's take a look at problem 7. So here we have negative 2 times the vector f, then minus 9 times the vector g. So we have f given to us in component form, where there's a horizontal component of 5 and a vertical component of negative 7. We have g in component form, which is given to us where negative 6 is the horizontal component and negative 6 is also the vertical component. So let me write this out. We have negative 2 times the vector f. And then what I'm going to do is put this as plus negative. I just think it makes it a little bit easier. So I'm going to go plus, and then you could wrap this in parentheses if you want for clarity. So plus negative 9 times your vector g. So to set this up, let's go ahead and say that we have negative 2 out in front of this guy right here. So the components inside, you have 5 and then negative 7. And then we're going to go plus, you're going to have negative 9. And then inside here, you're going to have negative 6 and negative 6 as your components. Okay, so let's put equals here. I'm going to multiply negative 2 times 5. That's going to give me negative 10. And then negative 2 times negative 7, that's going to give me 14. Let's close that down. Then I have plus. Negative 9 times negative 6 is going to be 54. And it's going to be duplicated here because you have the same thing. So let's just put a 54 here as well. So let's come down here a little bit, and I'll say this equals. To finish this up, let's add the horizontal components. So negative 10 plus 54, that's going to be 44. Let's add the vertical components. So 14 plus 54, that's going to be 68. So in component form, my resultant, or once again, if you want to call it the resultant vector, the horizontal component is 44 and the vertical component is 68. All right, let's take a look at problem 8. So here we have 4 times the vector A plus 5 times the vector V. So vector A is given to us in component form where the horizontal component is 12 and the vertical component is negative 7. Then vector V is given to us in component form where our horizontal component is 10 and the vertical component is negative 8. So let's write this out. We have 4 times the vector A, then plus 5 times the vector V. This is going to be 4 times this guy right here. So you have 12 and then negative 7 as your components. And then plus, you're going to have 5 times this vector V. So you're going to have 10 and then negative 8 as your components. So let's say 4 is going to get multiplied by each one of these components. So this would be 4 times 12, that's 48. And then 4 times negative 7, that's going to be negative 28. Then plus, you're going to multiply 5 by each component here. 5 times 10 is going to be 50. And then 5 times negative 8 is going to be negative 40. Okay, for the final step here, you're going to add the horizontal components together. So 48 plus 50 is going to be 98. And then you're going to add the vertical components together. So negative 28 plus negative 40, that's going to be negative 68. So my resultant, or once again, the resultant vector, if you want to call it that, in component form, the horizontal component is 98, and then the vertical component is negative 68. Okay, let's take a look at problem number 9. So here we have the negative of our vector u, then minus our vector b. Now we're not given the component form for the vector u, and we're not given the component form for the vector b. So we need to figure that out first before we can do this. So we're given the magnitude of the vector u. We're told that that's 10. We're given the direction angle for the vector u. That's going to be 184 degrees. Let me just copy this real quick and come down here. And remember, if you want to find the component form of the vector u, for the horizontal component, you take the magnitude, which is 10, and you multiply by the cosine of that direction angle, which is 184 degrees. Then if you want to find the vertical component, again, you take the magnitude, which is 10, and now you multiply it by the sine of that direction angle, which is 184 degrees. Okay, let's go back up. We're going to get the other guy. So for this one, the magnitude of the vector b is going to be 14, and then the direction angle theta is going to be 304 degrees. So let me copy that real quick and come down here. So for the vector b in component form, the horizontal component, again, just take this magnitude here, which is 14. Let me actually just put it there as well. So then here it's times cosine of the direction angle, which is 304 degrees. Here that magnitude is times the sine of, again, that direction angle, which is 304 degrees. All right, now before we continue, if you wanted a super accurate answer, then you could continue with things in this form. and just round at the end. Okay, I'm not going to do that. And so the answer I get is going to be slightly different than the practice test. So it's really not that big of a deal for your self-studying. If you're in a course and they're teaching this, you just need to ask your teacher what they want you to do, how accurate do they want your answer. So let's come back up and figure out what we need. So the negative of the vector u and then minus the vector b. So let me copy that and let's come down here. And I'm just going to paste this in here. So if you go 10 times the cosine of 184 degrees, let's say that's about, we'll go negative 9 point, let's just go ahead and say 98. Okay, so I chose to round to the nearest hundredth. You might choose to round to something else. Again, it's really up to you. So then the other guy, let's go 10 times the sine of 184 degrees in the calculator. I'm going to round that to the nearest hundredth and get about a negative 0.7. So let's say this is negative, I'll put 0.7 like this. Okay, so I put equals here. We know this is an approximation. You can use the approximately equal to symbol. It's really up to you. Again, if you're self-studying, it's not that big of a deal. So down here, let's go 14 times the cosine of 304 degrees. And if I round that to the nearest hundredth, I get about 7.83. So let's say 7.83. And then 14 times the sine of 304 degrees. Let's say that's negative 11 point, let's go 61. At this point, all I'm going to do is say that I want the negative of my vector u. And you can go plus negative 1 times the vector b, or you can just leave it as subtraction. It's up to you. Here it's pretty easy. Let's leave it as subtraction for once. So let's put minus the vector b like this. So what is this going to be? If you have a negative in front of something, you can treat that as just negative 1, right? So let me get rid of this, and I'm just going to put a negative 1 out in front of this vector here. So you have negative 9.98, and then you have negative 0.7. Let's close that down. And actually, let me drop this down because it's not going to fit over here. And I'm just going to put this like this. So you have your 7.83, and then your negative 11.61 like this. Okay. So what is this going to give me? Let me put equals here. So you're going to basically multiply each component here by negative 1, which is just a fancy way of changing the sign. So this right here would be positive 9.98, and this would be positive 0.7, or we could go 0.7 to stay consistent. And now you have minus, here you have 7.83, and then here you have negative 11.61. Okay, so far so good. What I'm going to do at this point is just subtract this guy minus this guy. Okay, so I'm going to go 9.98 minus 7.83. That's going to give me 2.15. And then here's where you have to be careful. You have 0.7 and then minus a negative 11.61. So let me write this out. 0.7 minus a negative 11.61. We know minus a negative is plus a positive. So this is like me doing this addition here. That's why I like to convert these things over to addition of the opposite. It just alleviates a lot of the sign mistakes. So let's go ahead and go 0.7 plus 11.61 in the calculator. And I'm going to get 12.31. So this would be my resultant vector in component form. The horizontal component is 2.15. The vertical component is 12.31. Now, if you are on the practice test, you may notice that this guy right here is slightly different, right? On the practice test, it's listed as 12.3. And again, this is just because the computer solved it in a different way. It's going to give you a more accurate answer. So either way, if you're self-studying, just get something that's close enough. If you're in a course, just ask your teacher, hey, where would you like me to round to, or what steps would you like me to take when I'm solving this problem so that I get the same result as you? Okay, let's take a look at problem number 10. So here we have 8 times the vector f minus 8 times the vector b. And you see we have the same setup as last time. So what I need to do is figure out, let me come down here, my vector f in component form. So this equals what? And then my vector b in component form. So this equals what? Okay, so we know that it's the magnitude times the cosine of the direction angle for the horizontal component, and then the magnitude times the sine of the direction angle for the vertical component. For the magnitude of f, it's 12. For the direction angle, it's 24 degrees. So this is going to be 12 times the cosine of 24 degrees, and this is going to be 12 times the sine of 24 degrees. So for this one, I get about, let's say 10.96. So 10.96 rounding to the nearest hundredth. And for this one, I get about 4.88 if I round to the nearest hundredth. So let's put that there. And again, I'll just say that if you're self-studying, you can put equals there. It's no big deal. But your teacher may want you to put an approximately equal to there. So that's really going to be up to you. So then for this one right here, let's go back up. For the magnitude of the vector b, it's 18. And then for the direction angle theta, it's 52 degrees. So this is 18 times the cosine of 52 degrees. This is 18 times the sine of 52 degrees. Let's key this into the calculator. So here, if I round to the nearest hundredth, I get about 11 point, let's say 0.8. And then here, I get about, let's say 14.18, again, rounding to the nearest hundredth. Okay, so coming back up, I want 8 times the vector f, then minus 8 times the vector b. Let me grab this real quick. And we'll come down here and just paste this in. And I'm going to convert this over to plus a negative there. So actually, let me write this a little bit better. So plus, you'll have negative 8 times your vector b like this. So this would be 8 times this guy right here. So you have your 10.96, and then your 4.88 as your components. And then you'd have plus, you have your negative 8, and then times this guy. So you're going to have your 11.08, and then your 14.18 as your components. So let's put equals here. 8 times 10.96, that's going to give me 87 point, let's say 68. Maybe make this 7 a little bit better here. And then 8 times 4.88, that's going to be 39.04. Let's put plus here. Negative 8 times 11.08, that's going to be negative 88.64. And then negative 8 times 14.18, that's going to be negative 113.44. Okay, so pretty easy at this point. We're just going to add these horizontal components. So 87.68 plus negative 88.64, that's going to give me negative, let's say 0.96. Then we're going to add these vertical components. So 39.04 plus negative 113.44, that's going to give me negative 74.4. Now, if you're on the practice test, again, because of rounding, the answer is slightly different. So you're going to get negative 0.95 there. Okay, so very close. And then negative 74.43 there. Okay, so this answer is fine. Again, when you use a computer for this, it's going to be more accurate. So the component form that we found, the horizontal component is negative 0.96, and the vertical component is negative 74.4. All right, let's take a look at the practice test. For the instructions, we're asked to find the unit vector u in the direction of the vector v. So for the first problem, we're given our vector v, and it's written as a linear combination of our unit vectors I and j. So we have to be comfortable with this notation because it's going to come up pretty often in math. So the vector v is equal to negative 4 times the unit vector I plus 8 times the unit vector j. So when you see a hat like that, that's telling you have a unit vector or a vector with a magnitude of 1. So what I'm going to do is use a little simple formula. My goal is to find a unit vector u, so let me just write that. And basically, it's going to have the same direction, or you can think about that as the direction angle, as this vector v, but the magnitude is going to be 1. So the formula is very simple. You just take your vector v, and you're going to multiply it by 1 over the magnitude of that vector v. So essentially, it's just going to scale it down to the point where it has a magnitude of 1. That's what you're trying to find, but the direction angle would be the same. So looking at this guy, remember how this notation works? If you want, you can write this in component form. So the horizontal component is going to be negative 4. It's what's multiplying that unit vector I. The vertical component is 8. It's what's multiplying that unit vector j. And so you can say that this is negative 4 and then 8 for the components times, we'll have 1 over, what's the magnitude of my vector v? Let me write that over here. So the magnitude of my vector v is the principal square root of, you have your horizontal component squared, negative 4 squared is 16, and then plus your vertical component squared, so 8 squared is 64. If we do 16 plus 64, that's going to give me 80. And of course, you could break 80 up into 16 times 5. So 16 is a perfect square, so this is going to be 4 times square root of 5. So 4 times square root of 5. So let's write that like that. Let's scooch down a little bit, and let's just say that this is equal to. You could put this out in front if it's more comfortable for you. So let me write 1 over 4 times square root of 5. And then times, you have this vector here with negative 4 and then 8 as the components. So let me slide down here a little bit. And so this guy is going to get multiplied by each. So essentially, you're going to have negative 4 over 4 times square root of 5. Let me put my bracket in there. And then you're going to have 8 over 4 times square root of 5. Okay, so let me put that like that. And let me come down here a little bit. I'm going to do some canceling. So this would cancel with this, and this would cancel with this and give me a 2. Let me write a 1 up there. So let's say that this is negative 1 over the square root of 5. Let me put my bracket in there. And this is 2 over the square root of 5. Now, a lot of times with these problems, you'll see people not rationalize the denominator. That's not something I'm really comfortable with. So if your book does this, then that's fine. I'm just going to take the extra step and rationalize the denominator. Let me actually slide this down here. So times the square root of 5 over the square root of 5. And let me do times the square root of 5 over the square root of 5. Let me close that down. And so this would give me, let me put my brackets in here. You have negative square root of 5 over 5. And then you have 2 times square root of 5 over 5. So this right here would be your unit vector u. So in other words, the magnitude is 1, and you can check that really easily. And it has the same direction as the vector v. So in other words, the direction angle is the same, and you could check that as well. Now, the way I've written it here is in component form. We were given our problem as a linear combination of the unit vectors I and j. So typically, you want to stick with the notation you were given. If you're given the problem in component form, answer in component form. If you're given the problem as a linear combination, answer as a linear combination. So what I'm going to do is just convert this over. I'll say this is equal to this right here. This negative of the square root of 5 over 5 is just going to be multiplied by the unit vector I. And then you're going to have plus this guy right here is going to be 2 times square root of 5 over 5. That's going to be multiplied by the unit vector j. So again, this would be your component form, and this would be your linear combination of the unit vectors I and j. All right, let's take a look at problem number 2. So here we have our vector v. It's given to us in component form. So the horizontal component is 30, and the vertical component is 40. Now, if you want to get some practice, again, you can just go back and forth between the two forms. So you can do a linear combination of the unit vectors I and j. So you could say this is 30. That's your horizontal component. That's going to be multiplied by the unit vector I. And then plus this is 40. That's your vertical component. That's going to be multiplied by the unit vector j. So again, just two different ways to write things. Now, if you want to find the unit vector u, again, that just means it has a magnitude of 1 in the same direction as this vector v, meaning the direction angle is the same. You're just going to take this vector v. So let me write this as 30 and then 40 for the components. And you're going to multiply it by 1 over the magnitude of that vector v. So what is the magnitude of the vector v? Well, again, you just take the square root of your horizontal component squared plus your vertical component squared. This might be something you want to key into a calculator because the numbers are pretty big. Let's just see what this is going to give us. So the result I get is going to be 50. And where that comes from, 30 squared is going to be 900. 40 squared is 1600. 900 plus 1600 is 2500. And if you take the principal square root of 2500, you get 50. So let's put 50 down here and let's slide down and we'll just do our multiplication. Again, this is going to be multiplied by each guy here. You can put it out in front. I think that makes people feel more comfortable. So 1 over 50, that's your scalar. And then these components, you have 30 and then 40. So let me make this bracket a little bit better here. And I'll just slide down here. Maybe I'll just bring the equals over here. So this would be 30 over 50, like this. And then this would be 40 over 50, like this. And of course, you can simplify that. So you can say that this guy right here is going to be 3/5, just canceling a common factor of 10. And this guy right here would just be 4/5, again, canceling a common factor of 10. So we write it like this in component form. We were given that guy in component form. But again, if you just want to practice, you could write this as a linear combination of the unit vectors I and j. So you could say this is 3/5. Again, that's your horizontal component, multiplied by the unit vector I, then plus 4/5. That's your vertical component, multiplied by the unit vector j. All right, for the next few problems, the instructions are going to change. Now we want to find the dot product, some people call this the inner product, of the vectors u and v. All right, so for problem 3, we have this vector u given to us in component form. So the horizontal component is -8, the vertical component is -3. Then we have this vector v, also given in component form. The horizontal component is 6, and the vertical component is also 6. So if you want to find the dot product, you would say this vector u, and then dot this vector v. All you're going to do is start by multiplying the horizontal components together. So in other words, negative 8 times 6. Then you're going to go plus. You're going to multiply your vertical components together. So negative 3 times 6, like this. And that's all it is. It's a very, very simple process. So we would say that negative 8 times 6 is negative 48. And then plus negative 3 times 6 is negative 18. So negative 48 plus negative 18, that's going to give me a result of negative 66. So that would be my dot product of this vector u and this vector v. All right, let's take a look at problem number 4. So here we have our vector u. So this is written as a linear combination of the unit vectors I and j. So we say this is equal to negative 9 times the unit vector I minus 2 times the unit vector j. So similarly here, this is a linear combination as well. So this vector v, this is going to be equal to negative 3 times the unit vector I minus 8 times the unit vector j. All right, so if we want to find the dot product, let's go ahead and say this vector u and then dot this vector v. Again, I'm going to multiply the corresponding components and then sum those guys together. So what I mean by that is you're going to take these horizontal components. So this is negative 9 times negative 3. And then I'm going to add this to, I'm going to take these vertical components and multiply those. So negative 2 times negative 8. Maybe I'll wrap this one for clarity. When you get negatives, it gets a little busy. All right, so let's say equals here. Negative 9 times negative 3 is going to be 27. And then basically you're going to have plus negative 2 times negative 8. That's going to be 16. And then 27 plus 16. That's going to give me a final answer of 43. So that's my dot product of this vector u and this vector v. All right, for the next problem, the instructions are going to change a little bit. We want to find the measure of the angle theta between vectors u and v geometrically. So looking at problem 5, we see we have this vector u given in component form. So the horizontal component is 8 and the vertical component is 3. Let me actually just write this here. So for the vector u, we have the horizontal component of 8 and the vertical component of 3. And then for the vector v, this is also in component form. So the horizontal component is 2 and the vertical component is 7. Okay, let me grab this real quick. And I'm just going to paste this in here. Before I start working with this sketch, I want to show you something. In the lesson, we looked at this formula here, but we didn't talk about where it came from. I just mentioned that it was from the law of cosines, but I want to show you this on an example. So the cosine of theta is equal to, you have the dot product of this vector u and this vector v, and this is over the product of these two magnitudes, right? So the magnitude of this vector u times the magnitude of this vector v. If you're using a textbook, you'll probably see a sketch like this. And basically, this is how you can derive this guy. You're going to use the law of cosines. So you're trying to find this angle here. Remember, with the law of cosines, you have this angle and the side opposite that are related, right? So something like, let's say a squared is equal to b squared plus c squared. And then we could say minus 2 times b times c times the cosine of that angle a. Okay, so something like this. Now let's go back up and let's think about this. So first off, you'll notice that this vector u and this vector v, they're both in standard position. So the initial point is at 0, 0 for each. Now for the vector u, the terminal point is at 8, 3. And then for the vector v, the terminal point is at 2, 7. So far that's pretty easy to understand. Now, this is where it gets a little bit tricky. You'll see that this vector here is denoted with the vector u minus the vector v. So if I had the vector u minus the vector v, that would be what? Well, I would subtract 8 minus 2, that would give me 6, and then 3 minus 7, that would give me negative 4. Okay, so this 6, negative 4 here, as a terminal point, if I started at the origin, would look something like this. So I'd go 6 units to the right, and then 4 units down, so it would be like this, and I would sketch this guy as something like that. Okay, so essentially what's happening is I'm taking this guy and I'm just shifting it here to where the initial point is now at 2, 7, and the terminal point is going to be at 8, 3. Okay, you can see that from 2, I would basically just be adding 6, so I'm going to the right by 6 units to get to 8. And then from 7, I'm subtracting 4 units away or adding negative 4, so I'm dropping by 4 units to get to a y location of 3. Okay, so that's all I'm doing. I'm just shifting this over here, and that allows me to complete this triangle. Okay, so now that we know where all this stuff is coming from, let me get rid of this. Essentially, you're just going to use the law of cosines. Before we use the law of cosines, we have to know a few things. So what is the length of this vector here, or the magnitude? So the magnitude of this vector u minus this vector v. How do we figure that out? Well, we can just use the regular distance formula because this point is 2 comma 7 and this point is 8 comma 3. This is the initial, this is the terminal. Okay, so we can say this is the square root of, you take your x sub 2 minus your x sub 1 quantity squared plus your y sub 2 minus your y sub 1 quantity squared. Okay, so in this case, let's just say this is 0.2 and this is 0.1. Again, you can reverse it, it won't matter. But let's erase this and just say that this is going to be 8 and then this is going to be 2. And then for this guy right here, this is going to be 3 and this is going to be 7. Now, what you're noticing here is we're getting 6 and negative 4, which is exactly what we got when we did our subtraction, right? So this is going to be 6 squared or 36. And this right here is going to be negative 4 squared or 16. So 36 plus 16, that's going to be 52. And you could write that as 4 times 13. So this would be 2 times the square root of 13 if you simplified it. Then we also need the magnitude of my vector v. So that's pretty easy. Again, the terminal point here is 2 comma 7. So it's the square root of 2 squared, which is 4, plus 7 squared, which is 49. 4 plus 49 is 53. So this is just the square root of 53. And then you'd have the magnitude of the vector u. So this is the principal square root of. You're going to take 8 squared, which is 64. And then plus 3 squared, which is 9. So 64 plus 9 is going to be 73. So this is the principal square root of 73. Now that we have this, let's go through and use the law of cosines. I'm just going to grab this real quick, and I want to paste this right here because we're going to need it in a moment. Let me actually drag this over so it's a little bit more in line. We're going to come back up here. So let's start out by taking the magnitude of this vector u minus this vector v. This would be squared. This would be equal to the magnitude of the vector u squared, and then plus the magnitude of this vector v squared. And then you would have your minus 2 times the magnitude of the vector u times the magnitude of this vector v. And then lastly, you're going to have times the cosine of that angle. Again, that's what we're trying to find, that theta there. Okay, and I know this is going on multiple lines here, but we'll clean this up in a moment. So again, you can see that if you related it back to what we already talked about, let's say you had this guy as a and this guy as angle a. So this would be a squared is equal to b squared plus c squared minus 2 times b times c times the cosine of a. So it's just the law of cosines. It's just rewritten. Again, for the side lengths here, you're using the magnitude, right? So this is a length that has the magnitude of the vector v. This has a length that's the magnitude of the vector u. This has a length that's the magnitude of the vector u minus the vector v. So that's all it is. Okay, so let's get rid of this and let's grab this real quick. And let me paste this in here. And I'm just going to do a lot of cleaning up. So let's try to write this in line. So we have the magnitude of the vector u minus this vector v, and this is going to be squared. And this is equal to, we have the magnitude of the vector u being squared plus the magnitude of the vector v being squared. So let me get rid of this part right here. And I'm going to actually slide this down. And we can get rid of this border now if we want. And then I'm just going to actually move this up here. Don't need to rewrite it. So it all fits on one line. Okay. Let me put my border back in here. So if I squared this guy, this is 2 times square root of 13. Okay. So this is 2 times square root of 13. And I'm going to square that guy. And this equals, this guy right here is the square root of 73. And I'm going to square that guy. So let me write the square root of 73. And I'm just going to square that. And then plus, I'm going to have my square root of 53. And that's going to be squared. So that's coming from the magnitude of the vector v being squared. And then I'm just going to go minus 2 times. Again, the magnitude of the vector u is the square root of 73. And then the magnitude of the vector v is going to be the square root of 53. And then lastly, it's times the cosine of my angle theta. Let me get rid of this. And actually, you don't need that anymore. It's just basically calculations at this point. And let me rewrap that and slide this down here like this and slide this up here like this. So for this one, 2 times square root of 13 being squared, 2 squared is 4. And the square root of 13 being squared is 13. So 4 times 13, that's going to give me 52. And this equals the square root of 73 squared is 73. And then plus the square root of 53 squared is 53. And then minus 2 times the square root of 73 times the square root of 53 times the cosine of theta. So you want to solve this for the cosine of theta. And to do that, I would say 73 plus 53, that's going to be 126. So let me write that in there. And I'll say 52 minus 126, that's going to be negative 74. So this becomes negative 74 is equal to negative 2 times the square root of 73 times the square root of 53, and then times the cosine of theta. Now again, if I want to solve for the cosine of theta, I'm just going to divide both sides of the equation by -2 times the square root of 73 times the square root of 53. So let me do that over here as well. So let's go -2 times the square root of 73 and then times the square root of 53. Okay, so this is going to cancel, and I'm going to write this cosine of theta on the left. So let's say the cosine of theta is equal to, so you have -74 divided by -2. So let's go ahead and do that on the calculator, and I get 37. So let's say this is 37 over the square root of 73 times the square root of 53. Now let's stop for a moment. Before we calculate this, I want you to remember the formula that we had. The cosine of theta is equal to, you had the dot product of the vectors u and v. Let me make that v a little bit better there. And then over the magnitude of u times the magnitude of v. What's the dot product of these guys? So u dot v. What is that going to be equal to? Well, you have 8 times 2, that's 16. And then plus 3 times 7 is 21. 16 plus 21 is going to be 37. So coming back, notice that's what you have here, the dot product of u and v. Now what about this? Well, the square root of 73 is the magnitude of the vector u, and the square root of 53 is the magnitude of the vector v. So here you see that you came up with your formula. Now, if you wanted to do it with that generic sketch, you can. That's one way to prove it. But I think that doing it with an actual example is a little bit easier to comprehend, and also it makes the math a little bit more manageable. Okay, so at this point, all you're going to do is say that theta is equal to the inverse cosine of this guy right here, so 37, over your square root of 73 times your square root of 53. Let's key that into the calculator and just try to be extra careful when you enter this in. You're going to get about, let's say 53 point, let's go ahead and say 5 degrees. So that would be the angle between the vectors u and v. All right, for the next few problems, the instructions will change. Now we want to find the measure of angle theta between vectors u and v. So for problem 6, we have our vector u given in component form. So the horizontal component is 2 and the vertical component is -4. Then we have our vector v also given in component form. So the horizontal component is 4, the vertical component is -5. So remember our little formula here. It's not that tough to remember. Maybe you have to write it down a few times. So the cosine of theta is equal to, you're going to have the dot product of these two vectors. So u dot v, like this. This is over. You're going to have the magnitude of your vector u times the magnitude of your vector v. So first I'm going to figure out the dot product of the vectors u and v. So to do that, again, we'll go u dot v. This is equal to, you're going to multiply the horizontal components together. So 2 times 4 is going to give me 8. And then plus, multiply the vertical components together. So -4 times -5 is 20. So 8 plus 20 is going to be 28. So this right here is going to be 28. Very easy. Now, for the magnitude of the vector u, this is going to be what? The square root of, you take 2 squared, that's 4, and then you add that to -4 squared, that's going to be 16. So this would be the square root of 20. Now this would break down into 4 times 5, and so this is 2 times square root of 5. So 2 times square root of 5, so let's write that right there. This is 2 times square root of 5. And then for the magnitude of the vector v now, this is the square root of, again, you take 4 and square it, that's 16, and then plus -5 squared, that's going to be 25. So 16 plus 25, that's going to be 41. So this right here would be the square root of 41. Okay, so thinking about this, you could just key this into your calculator and say that theta is equal to the inverse cosine of, you can go 28 over. Now you could multiply this together. 5 times 41 is 205, so you could say this is 2 times the square root of 205. It's not necessary, but it might make it a little bit easier to punch it into your calculator. Again, that's really personal preference. So this is approximately what? Let's just key it in. And I get about 12.09, let's say, degrees. I'll just round it to the nearest hundredth. Again, if you're having problems when you punch this into your calculator, you get something like a domain error, make sure you wrap things in parentheses for clarity. Some calculators are good about it, and other ones you really have to be specific. So for the angle between the vectors u and v, we get about 12.09 degrees. All right, let's take a look at problem 7. So here we have the vector u, which in component form has a horizontal component of 2 and a vertical component of 9. And then we have our vector v, which in component form has a horizontal component of 8 and a vertical component of -3. So again, it's just a little simple formula. Let's just go ahead and say that the cosine of theta is equal to the dot product of these vectors, so u dot v, and this is over the magnitude of u times the magnitude of v. So let's figure out what is the dot product first. So u dot v is equal to what? So I'm going to multiply these horizontal components together. So 2 times 8 is 16, and then plus, I'm going to multiply these vertical components together. So 9 times -3 is -27. So 16 plus -27, that's going to give me -11. So let me put this up here as -11. Let me get rid of this. And now we're going to think about the magnitude of the vector u. Again, that's the square root of 2 squared plus 9 squared. So 2 squared is 4 plus 9 squared is 81. So this would be the square root of 85. Now 85 divided by 5 is 17, so you really can't do anything with that. So this would just be the square root of 85. And then for this guy, we want the magnitude of the vector v. So this is going to be what? It's the square root of 8 squared, which is 64, plus -3 squared, which is 9, and 64 plus 9 is going to be 73. So this would be times the square root of 73. Let me make this 3 a little bit better here. All right, let's get rid of this. Now, again, you could punch this in your calculator like this, or you can multiply 85 times 73, and you would get 6,205. So this would be the square root of 6,205. And make that a little bit better there. So in your calculator, let's say that theta is equal to the inverse cosine of this guy right here. So -11 over the square root of 6,205. Again, be very careful about how you key this in, because you might get a domain error if you're not specific. If I round to the nearest hundredth, I get about 98.03 degrees. So that's going to be the approximate angle between these vectors u and v. All right, let's take a look at problem number 8 now. So here we have our vector u. This is now written as a linear combination of the unit vectors I and j. So we have the negative of the unit vector I minus 3 times the unit vector j. And then for the vector v, it's written in the same way, so as a linear combination. So here this is equal to 3 times the unit vector I plus 8 times the unit vector j. So again, the formula is the same. So we have the cosine of theta is equal to, you're going to have the dot product of your vector u and v over the magnitude of u times the magnitude of v. So let's start with this dot product here. Again, you can write this in component form if you're more comfortable. You could put a little -1 there if that helps you out. So the dot product of u and v, so u dot v is equal to what? So -1 times 3, that's -3, and then plus -3 times 8, that's going to be -24. So this would end up giving me -27 as a result. So let's put this up here as -27, and let's get rid of this. Okay, the next thing is you want the magnitude of u and the magnitude of v. So what is the magnitude of u? Well, I just want the square root of, again, this is your horizontal component, so it's -1, and I'm going to square that, plus this is your vertical component. Make sure you take that minus with you. You can always go plus negative if you're having trouble with that. So this is going to be -3. That's going to be squared. So -1 squared is 1, and then -3 squared is 9. So this would be 1 plus 9, which is going to be 10. So this is the square root of 10, and we can just write that in right there, like this. And then we want the magnitude of the vector v. So again, the square root of, you've got 3. You're going to square that, you get 9. And then plus, you've got 8. You're going to square that, you get 64. And so 9 plus 64 is going to be 73. So the magnitude of the vector v is going to be square root of 73. Okay, let's get rid of this. And let's think about this. So you could punch this into your calculator again as is, or you could multiply first. So you could say this is the square root of 730. And so let's go ahead and say that theta is equal to the inverse cosine of -27 over the square root of 730. Close that down. So this is approximately, I get about 177 point, let's say 88 degrees if I round to the nearest hundredth. So the angle between my two vectors u and v is going to be about 177.88 degrees. All right, let's take a look at problem number 9. So here we have our vector u, which is written as a linear combination of the unit vectors I and j. So this equals -3 times the unit vector I plus 5 times the unit vector j. And then our vector v, again, written as this linear combination of the unit vectors I and j. So it equals 3 times the unit vector I minus 8 times the unit vector j. All right, so once again, we would just think about our simple little formula. The cosine of theta is equal to, you have the dot product of u and v. So let's just do this on the fly. So we know this is negative 3 times 3. That's going to be negative 9. And then plus, you have 5 times negative 8. Again, always take this sign with you. So 5 times negative 8 would be negative 40. So this right here would be negative 9 plus negative 40. That's going to be negative 49. So that's your dot product for u and v, those two vectors. Okay, this is over the magnitude of u. So for that one, it's going to be the square root of, you have negative 3 squared, which is 9, and then plus 5 squared, which is 25. So 9 plus 25 is 34. So this is the square root of 34. Now 34 is 17 times 2, so you really can't do anything with that. The other guy is the magnitude of the vector v. So this is the square root of, you have 3 squared, which is 9, and then plus negative 8 squared is 64. And we know 9 plus 64 is going to be 73. So this would be the square root of 34 times the square root of 73 down here. Again, you can key this into your calculator, or you can say 34 times 73. That's going to be 2,482. So you can just say this is the square root of 2,482 down here. In my calculator, I'll say theta is equal to the inverse cosine of this guy right here, so negative 49, over the square root of 2,482. Close that down. So this is approximately, if I round to the nearest hundredth, I get about 169 point, let's say 59 degrees. So my angle between the vectors u and v would be about 169.59 degrees. All right, for the next few problems, the instructions tell us to determine if the vectors u and v are orthogonal. So what that means is basically that you have perpendicular vectors, or the angle between the vectors is going to be 90 degrees. So thinking about the formula for the angle between two vectors, so the cosine of theta is equal to, again, you have the dot product of this vector u and this vector v, so u dot v like that. And then this is over the magnitude of the vector u, and that sort of looks like a v, so let me clean that up, and then times the magnitude of the vector v. So what happens is, if you have orthogonal vectors, the angle theta is going to end up being 90 degrees, right? So those guys will end up being perpendicular. So that happens when this guy right here, this dot product, is 0, okay? Because this will be 0 over something that's not 0. So you get 0 as a result there, and basically your theta there is going to be 90 degrees. Okay, so thinking about this, we have our vector u in component form. We have a horizontal component of negative 5 and a vertical component of negative 2. We have our vector v in component form. We have a horizontal component of negative 2 and a vertical component of negative 5. So if we do u dot v like this, again, all we're going to do is multiply the horizontal components together. So negative 5 times negative 2, that's positive 10. And then plus multiply the vertical components together. So negative 2 times negative 5, that's going to be positive 10. So this becomes 10 plus 10, which is 20. So that's not 0. So we can just say no. These are not orthogonal vectors. Okay, let's take a look at problem number 11 now. So again, we want to determine if they are orthogonal vectors. So here we have our vector u written as a linear combination. So this is going to be equal to 9 times the unit vector I minus 4 times the unit vector j. Then we have v that's also given as a linear combination. So this is equal to negative 8 times the unit vector I minus 18 times the unit vector j. Okay, so the first thing we would figure out is, what is the dot product? So we're going to go u dot v like this. So you're going to multiply this guy right here. So the horizontal component is 9 times the horizontal component here, which is negative 8. So 9 times negative 8 is negative 72. And then plus, here I'm going to go plus negative and plus negative, so I don't make a sign mistake. So your vertical components would be multiplied together. So negative 4 times negative 18, that would be positive 72, and so this is 0. So this tells me that yes, we do have orthogonal vectors. And again, you can just plug into the formula and see that the angle between the vectors would be 90 degrees. So cosine of theta is equal to, this would be 0 here. So this leads to saying that theta is going to be equal to 90 degrees. So we know that these are orthogonal vectors.